So the last box we have to check before we qualify the May equation as generating chaos was the one that is in some ways the most interesting, which is that even though detailed prediction is impossible, it is possible to talk about the causes of chaos. Or if you prefer, the mechanisms. So you remember in the Hastings model, the food chain, Z eats Y, Y eats X, we could talk about the cause of chaos. And the cause of chaos was contained in the idea of two feedback loops, the herbivore plant feedback oscillation and the carnivore herbivore feedback oscillation. And the combination of the two of those, let me just remind you, produced this attractor. X and Y oscillate, Z grows until Z crashes. And here is X and Y and Z. And X and Y oscillate, and Z grows, and then Z crashes and begins a new oscillation of X and Y. It was possible to talk about, in broad terms, the mechanisms that are producing chaos in the food chain model. So what are the causes of the chaos in the May equation? Well, let's begin. Let's describe it. Xn plus 1 equals R times Xn times 1 minus Xn. The first thing we should do is let's graph this function. So here's Xn. It's going to go between 0 and 1. And let's put Xn plus 1. So Xn plus 1 equals f of Xn. We can therefore graph this function, and it's a graph of f. So let's graph this function, and let's ask, what does that graph look like? The answer is very interesting. It looks like this, where that is 1 right there. It's an inverted parabola. It's a parabola because it has an x squared, and it's inverted because that x squared has a minus sign. So this is the graph of Xn plus 1 equals R times Xn times 1 minus Xn. Now, in order to understand what this graph means, I want to go back and look at our linear example of a discrete time system. So you remember what that is, and I'm actually going to close this unit square here. And I want to draw a line, a guidance reference line, and that is that line. And that is, since this is Xn and this is Xn plus 1, that dotted line is the graph of the function Xn plus 1 equals Xn. This is the graph of the function y equals x. That is to say, Xn plus 1 equals Xn. So notice that every point on this line is an equilibrium point. If indeed the function ever crossed that line, it would be an equilibrium point of that function. Now, in the case of the linear functions, First of all, let's do xn plus 1 equals 1.1 times xn. What does that look like? Well, that's a straight line, passes through 0, and has slope 1.1, whereas this has slope 1. This has slope 1.1. It's more steeply sloped. So how many equilibrium points does this have? We already did this algebraically, but we confirmed this graphically. How many times does the blue line cross the yellow dotted line? The answer is once at 0. And this is a model of an infinitely growing population. Conversely, if I chose xn plus 1 equals 0.9 times xn, this is a line of slope 0.9. It also crosses the dotted line at exactly 1 point, which is 0. And this model simply says that xn will decline with passing time, will decline, and its slope is less than 1. Now, with that in mind, what is this telling us? Well, there is a region here with positive slope. That positive slope could be greater than 1. It could not be greater than 1. And the key there is the value of r. I drew an r here. I drew a parabola here, which is typical of r equals 2 or 2.5. If r is 1.5, it's a much more shallow parabola that never actually intersects the equilibrium point. It stays under that dashed line. And so you just go right to the equilibrium point at 0. For r equals 2, it gets taller. For r equals 3, it gets still taller. And for r equals 4, it is just tangent to the top of the box. So we have a family of parabolas of increasing height. Now that has a consequence. First of all, let's look at this and ask ourselves, what are the dynamics here? The first point is answered by let's just look at what this function is doing. Permit me to redraw it. And I'm going to draw a fairly high value of r. And what is this telling us about the dynamics? Well, number one, there is an equilibrium point. At this equilibrium point, because it's lying on that diagonal, we know that xn plus 1 equals xn. That's the definition of an equilibrium point. So there is an equilibrium point here. Now, the overall dynamics can be summarized by realizing that if you start with a small value of x, well, your next value is going to be bigger. Why? Because this parabola is lying above the 1, 1 line. That means you're getting back a bigger xn plus 1 for your xn. So this whole part of the curve here, we can call the growth part. If you're here, you get bigger. If you're here, you get bigger. If you're here, you get bigger. Even if you're here, you get bigger because this is still above the equal money line. And so in this whole section here, xn plus 1 is bigger than xn. That is for everything less than the equilibrium point. On the other hand, once you land on this arm of the curve, and you have to land on that arm of the curve, because if you weren't, you would be growing. If you start here, you grow and you grow and you grow, and you have to grow to such a point that you're on the other arm, and now the other arm is a shrinking arm. It's a crowding arm. And here is the crowding term. And so the causal story here, the cause of chaos here, is that the state point is being hit back and forth like a tennis ball between the growth phase and the crowding phase. And the growth phase inevitably takes you to the crowding phase. And then the crowding phase, xn plus 1 is less than xn because it's below the equal money line. Xn plus 1 is less than xn. So if you're in the crowding phase, you will shrink and eventually get thrown back into the growth phase. So it's a yo-yoing back and forth between the growth phase and the crowding phase. That's the mechanism of the variability here.